All right, today we're going to dive into two of the absolute cornerstones of physics, scalars and vectors. Now, these are the building blocks for describing pretty much everything, from how fast a car is going to the pull of gravity. And trust me, getting the difference between them is a total game changer. So, to get our heads around this, let's kick things off with a little puzzle. Imagine you're at a theme park and you get on one of those giant Ferris wheels. The ride takes you around and around and around. You're traveling a massive distance. But when the ride finally stops, you're somehow only a few steps from where you got on. How on earth is that possible? Well, here's the deal. The total path you traveled, every single meter you moved along that circular track for 7.5 revolutions, that all adds up to 330 meters. That's a serious journey. But your final position is just on the opposite side of the wheel from your starting point. And because the wheel is 14 meters across, you're only 14 meters away. This little paradox gets right to the heart of what we're talking about today. You see, those two numbers, 330 meters and 14 meters, they're describing two completely different things. One is the total journey you took, the how much. The other is your final location relative to the start, the where. This really highlights a key idea in physics. Sometimes just a number isn't the whole story. Sometimes you absolutely have to know the direction too. Okay, first up, the easy one, the scalar. A scalar is just a number. That's it. It tells you the how much or the how big of something. It's got magnitude, a size, but absolutely no direction attached. The thing is, we use scalars all the time without even thinking about it. You know, when you say a car is going 50 miles per hour, that's a scalar. When you check the weather and it's 20 degrees Celsius, or say an object has a mass of 5 kilograms, you're using scalars. They're just simple, straightforward numbers. And now, for the star of the show, the vector. This is where things get really interesting. A vector takes that simple scalar number and adds a crucial piece of information: direction. It tells you not only how much, but also which way. Think about it. You don't just push something, you push it in a specific direction. Your weight is a force that's always pulling you downwards. And that 14 meters on the Ferris wheel, that's a vector we call displacement. It's the straight line distance and direction from your start to your finish. That which way part is what makes it a vector. Okay, this is a classic mix-up, but it's the perfect test to see if this is all clicking. Speed and velocity sound so similar, so why are they treated so differently in physics? It all comes down to that one little extra detail: direction. Speed is the scalar. It's just the number on your speedometer. Simple as that. Velocity is the vector. It's your speed and the direction you're going. It's like a weather report. Saying a storm is moving at 30 kilometers an hour isn't all that helpful. But saying it's moving at 30 kilometers an hour north, that's velocity, and that's information you can actually use. So if vectors have this whole direction thing going on, we obviously can't just add them up like regular numbers. So what happens when you have multiple forces or motions at play? How do we figure out the combined effect, what physicists call the resultant vector? Well, the easy cases are when they're all lined up. If two forces are pulling in the exact same direction, you just add their sizes together. So 20 newtons plus 30 newtons gives you a total force of 50 newtons. And if they're pulling in opposite directions, you just subtract one from the other. Here, a 30-newton force easily overpowers a 20-newton force, leaving you with a net force of 10 newtons in the stronger direction. But this is where it gets really fun. What happens when the vectors aren't in a straight line? What if they're acting at an angle to each other? You can't just add or subtract them anymore. This is where we have to start thinking a little more visually. Let's take a look at a classic example. You've got a ship, and its engine is pushing it due north at 12 kilometers per hour. But at the same time, there's a strong sea current pushing it due east at 4 kilometers per hour. The ship isn't just going to go north, and it's not just going to go east. It's going to end up somewhere in between. So how in the world do we figure out its actual path? The trick is to actually draw it. We draw an arrow for the ship's northward motion. Then from the tip of that first arrow, we draw another arrow for the eastward current. This is what we call the head-to-tail method. The ship's actual path, the resultant, is a straight line from the very start of the first arrow to the very end of the second one. And look at that. We've just made a perfect right-angled triangle. Now we just need a little bit of high school math. Pythagoras' theorem will give us the actual speed, and some basic trigonometry will tell us the exact direction. So we crunch the numbers, and there it is, the ship's true velocity. It's actually moving at 12.6 kilometers per hour. at an angle of 18.4 degrees east of north. By combining those two separate vectors, the engine and the current, we found the single vector that describes the ship's real motion. Pretty cool, right? Okay, so we've seen how we can add vectors together to get one single result. But what's really cool is that we can do the exact opposite too. We can take any single vector and break it down into two separate parts at right angles to each other. This is called resolving a vector, and it's an incredibly powerful tool. This is the big idea right here. Any force that's acting at an angle is kind of secretly doing two things at once. It's acting horizontally, and it's also acting vertically. Resolving a vector is just our way of figuring out exactly how much push or pull it's contributing in each of those two directions. And guess what? We use the same tool, the right-angled triangle. Only this time, our main vector is the long side, the hypotenuse. The other two sides, the horizontal and vertical ones, are its hidden components. And with a tiny bit of trigonometry, we can find their exact sizes. The horizontal part is always the main force, times the cosine of the angle. And the vertical part is the force times the sine of the angle. Let's look at a real-world example to see this in action. A glider is being towed by a cable, and that cable is pulling with a tension of 620 newtons at a 25-degree angle. That single force is actually doing two jobs at once. When we resolve it, we find out it's providing 560 newtons of force to pull the glider forward and 260 newtons of force to lift it upwards. So that brings us to the big question. Why does any of this matter? Why go through all the trouble of adding and resolving and using trigonometry? Well, the simple answer is, without vectors, we just can't accurately describe our world in motion. It's as simple as that. I mean, think about it. From a pilot navigating a plane in a crosswind to an engineer designing a bridge that has to withstand forces from all kinds of directions, vectors are absolutely essential. They let us combine lots of different influences to find out what will actually happen. And they let us break down super complex problems into simple, manageable parts. They're basically the language of motion and forces. All right, let's wrap this up with a classic question, the kind you might see on an exam, to really nail this down. A runner sprints one full lap around a standard 400-meter athletics track. Think about it for a second. What is the total distance they've traveled, and what is their final displacement? Okay, so the distance, the scalar, that's the total path they covered. Easy, that's 400 meters. But the displacement, the vector, is the change in their position from their start point to their finish point. And since they ended up in the exact same spot where they started, their displacement is 0. And that right there is the whole story. It really makes you wonder, doesn't it? In how many other parts of life is the path you take just as important as where you end up?